So I wanted to talk a little bit about 2 and 3. And what they were doing there is they were adjusting those equations we were working on yesterday. Remember, we had developed that equation where the amount in Social Security, if they estimated it, if it reached the 3 trillion, would be 3 trillion in 2032. And then it was going to decrease by 8.7%. So that's 100 minus 8.7 is 0.913, and then to the power of t. So where t is years after 2032. Now, what they're asking here for number 2, if the funds do not reach the 3 trillion, but instead are 10% less than 3 trillion. So what we have to do is we're going to reduce by 10%. So reducing by 10%, if you recall, is 100% minus 10% is 90%, or 0.9. So we could take our original 3 trillion, that's this number here we're adjusting, times 0.9 gives us 2.7 trillion. So the new formula there would become A equals 2.7 times 0.913 to the power of t. And that's what you would use in number 2. Number 3 was a little bit trickier. In number 3, what they're saying is it still it reaches the 3 trillion. So we still have this formula. But what's different this time is the rate of change. It's declining by more than 8.7%. It is 10% greater than. So this is a 10% increase. So this is 100% plus 10%. We're looking at 110%. But it's not the balance that's 110%, it's the rate of change that's changed by 110%. So what we're doing is adjusting that 8.7% by that 110%, so multiplying by 1.10, which is going to give us 9.043. Okay. Oh, careful, 9.57, right? You're a step ahead of us. You're the 0.9. Yep. That's okay. So that's 9.57%. So this number in here, the 0.913, is going to be replaced by 100% minus the 9.57%, equals 90.43%. So our new formula then becomes, the amount is, we're back to the 3 trillion, but it's instead of 0.913, it's 0.9043, as you said. Okay, let's take a look. Number 2, what is the new estimated value of the funds? So we're going to go back up to number 2 here. What's the estimated value in 2040? So that's after 8 years. So we're using this adjusted formula and putting in 8 for t. So 2.7 times 0.913 to the power of 8. I'm getting 1.304 trillion. Now I believe Quantway wanted is 1,304 billion or something like that. Nope, for number 2 it's 2.7 trillion. Nope. Yep, on quantity it wants billion. So to make it billion, you've got to move it over 3 spots. It's 1,304 billion. Yep. Yeah, we'll do number 3 here in a second. So number 3, actually, just we'll do it now. Any more questions on number 2? Sam, did you figure that out? Does that make sense? Yeah, to get from trillion to billion, it's just moving a decimal point. It's almost like metric prefixes. Okay. Well, part B. Well, let's see. All it's asking us to do is, what's the change? Okay. This is actually something you don't even really need to calculate. If the start in an exponential model, if the starting value is 10% less, the value at every year is going to be 10% less. If we were to do a table, the starting value doesn't change this factor right here. This 0.913 to the power of t is going to be the same every year, no matter what the starting value is. So whatever percent you change the starting value, that's the same percent every year changes. Yep. Okay, number 3. What is the new estimate value of the funds in 2040? So we're back to using 3 trillion, but it's 0.9043 now. And it's to the power of 8 because it's 2040. So 3 times 0.9043. And I'm hoping Quantway didn't round this funny or anything like that. I got 1.342 trillion, which is 1,342 billion. Yeah, it's 13415. So that would round to 1.342. Does it ask, when it says enter whole or decimal, does it say trillion or billion after it? Billion? So it'd probably be this one. The 1.342 is what I would enter. Okay. Well, let's look at part B. Complete this. Go ahead. Okay. So complete this sentence here, round to the nearest whole percent. The estimated value in 2040 after a yearly decline of 9.57 is 0.8% less than it was before. Okay, so now we're going to do this with back to the 0.913 that we had before and compare this. So 3 times 0.913, the power of 8, was 1.448 trillion, or 1,448 billion. So this is considered the old amount. This is the beginning value. This is considered the new amount. That's after we change the percent. So to get that percent change, it's the 1342 minus the 1448. What goes on bottom is the 1448. So we subtract there, what is that? Negative 106? Is that what it comes up to be? Yep, 0.073. So yeah, 7.3% about. They want to the nearest whole percent, so it'd be 7%. Okay. It's just kind of funny wording the way they worded that of decrease the balance by 10% or increase the rate of decline by 10%. Sure. So I just wanted to clarify those a little bit before we moved on today. So remember, you have that out of class exercise, M7, and the PNL for M8 will be due tomorrow. Number 4, let me take a peek. So set the value funds was 10% less and rate of decline was 10% greater. Okay, so what number 4 is asking us to do is to do both. So our original was 3 times 0.913 to the power of t. They want us to both make this 10% less, which is the 2.7, and make this 10% more, which is the 0.9043. And then find the value in 2040. So that means make t equal 8 and figure it out. So it's going to be much less. Okay, so the preparing for next lesson here for M8 was a lot of articles about weight loss and calorie expenditure and stuff like that. And what we want to start off with today is we're going to talk about that resting energy expenditure. Resting energy expenditure is the number of calories you burn per day without exercising. So the problem is when you're dealing with the human body, there's all sorts of theories and formulas out there, and all of them are just estimates. So there often are several different ways or several different estimates that have been developed by different people with varying degrees of accuracy. So we're looking now here in M8. This is on the second page or so, where it says problem situation 1, investigating models for resting energy expenditure. Resting energy expenditure, we're just going to refer to as REE from here on out, so I don't have to write that whole thing out. But what we're looking at is there's actually several models. There are 4 different models, one by the American College of Chest Physicians. Another model is the Harris-Benedict model. That one actually separates it out for male or female. And then the Penn State has 2 different models they've published. The simple model we have, this is M8 problem situation 1, is from the American College of Chest Physicians. The resting energy expenditure is equal to 25 times your weight, where W, of course, is your weight, and weight has to be in kilograms here, not pounds. Hold on. Thank you. So, first of all, what type of a model is this? We've talked about 2 types of models, linear and exponential. Would this be linear or exponential? Linear, very good. I don't know where my L went. It is linear because it is a constant rate of change. Remember, exponential is named because it has a power in it somewhere. You know, we'd have some sort of a number with x or t is the power of that exponent. So it can't be exponential. It has to be linear. And it's a constant rate of change here. Now, there is no starting point. The starting point, you know, that y-intercept that we talked about isn't here. We could think of that as being plus 0, which makes sense because if you have no weight, you're not burning any calories. The rate of change for this model, if your weight increases by 1 kilogram, how many more calories do you burn in a day? Well, let's check it out. Let's look at somebody who is 80 kilograms compared to someone who is 81 kilograms. If it was 80 kilograms, this would give us 25 times 80, which is what? 25 times 80 is 2,000 calories. Good. If it was 80, the person was 81 kilograms, it's 25 times 81, which is how many? 2,025. So adding 1 kilogram of weight or mass to a person increased the calorie use by how much? 25. So the rate of change here is 25 calories. Okay, I'll try to adjust the mic there. So it's 25 calories per 1 kilogram is the rate of change. So every kilogram of change in mass or weight gives us 25 calories difference in energy expenditure per day. Now that's a pretty simple and easy estimate, but simple usually isn't the most precise, most accurate. So there are several other models that have been given there. You can see the Harris-Benedict. The Harris-Benedict model has a lot more variables in it. The Harris-Benedict model considers not only your weight, it also considers your height and your age. Height and weight actually come into play because it's your body surface area. The amount of skin you have in your body affects your calorie burning. So in the Harris-Benedict model for men, your resting energy expenditure is 66.4730 plus 13.7516 times the weight. I'm just going to put in W for weight. Plus 5.0033 times the height. I'm just going to use H for height. And then minus 6.7550 times your age. This is also found, by the way, right in your packet. So if you don't have these down, you don't have to write them down or anything. But there are three things here, that the Harris-Benedict model is saying affects your resting energy expenditure. There's weight, height, and age, all in the formula. Looking at the formula, I want you to just take a few seconds and then we'll answer this in a little bit. But I want you to think, looking at the formula, does weight increase or decrease? If your weight goes up, does that increase or decrease your energy expenditure according to this formula? Okay, so what would you say? If weight increases, does the energy expenditure go up or down? Well, this is a positive rate of change, yes. So this is actually, if you hold the height and the age constant, this would be a linear model of weight. With a constant rate of change, it's positive, so it would increase with the weight. So if your weight goes up, that's called if your weight goes up, the energy expenditure goes up. That's called a positive relationship. So how about for your height? Is that a positive or negative relationship on your height? Yes. If your height increases, your energy expenditure would also increase. How about for the age? That's a negative, yes. Because it's a negative number multiplying the age, As the age gets larger, the energy expenditure gets smaller. Now, they do have a separate formula in the Harris-Benedict model for females. Come on now. The female model, resting energy expenditure, is 655.0955 plus 9.5634 times the weight plus 1.8496 times the height minus 4.6756 times the age. Now, as we look through this one, is weight a positive or negative relationship? Weight is positive again. Height, positive or negative? Positive. And age, positive or negative? Age is still negative. So it's the same type of relationship, but you'll notice the strength of the relationship is different. If a male increases their weight by 1 kilogram, does that change their energy expenditure more or less than it would for a female who increases their weight by 1 kilogram? Okay, if we increase the weight, goes up by 1 kilogram, would that have more of an effect on the resting energy expenditure for a male or for a female? Well, look at the numbers before them. Yeah, I kind of gave that one away, didn't I? If you look at it, for males, it's 13 times the weight. For females, it's only 9 times the weight. So 1 kilogram change only has a change of 9 for women and 13 something for men. If you look at the height, there's a similar relationship, and the age, there's a similar relationship. What do you think this number here means? That's not multiplying the height, the weight, or the age, or anything. It's just there is a number. What do you think those numbers mean? Not necessarily 60%. That's your base calorie intake, or calorie expenditure, I should say. So men, what this is saying is this number is really small for men. So it's saying is for men, their calorie expenditure is more variable. Their calorie expenditure depends more on their weight, height, and their age. Whereas for women, this number is large. Think of that as like your y-intercept. Women are going to burn close to that number of calories, and you can see the weight, the height, and the age have smaller effects on their calorie expenditure than they do for men. Okay, so let's get back onto the task here for the formula. We've actually already kind of done number one, which equations have a positive effect, or which variables have a positive effect. We saw the weight and the height have a positive effect, and the age has a negative effect. I do need to get one more equation out there. That's or actually two more equations. The Penn State equations. Penn State created an equation in 1998. And their 1998 equation is the resting energy expenditure is 1.1 times, I'm just going to do the HB value, plus 140 times Tmax is your maximum body temperature in a 24-hour period, plus 32 times VE, That's your volume of your inhaled and exhaled air minus 5,340. In that equation, which values have a positive effect? If your Harris-Benedict value goes up, does that increase your resting energy expenditure? Yes. If your body temperature goes up, does that increase your energy expenditure? Yes. If the volume of air you inhale and exhale goes up, does that increase your energy expenditure? Yes. And how did we know that those all increase? Because they're positive numbers. Exactly. Now, Penn State revised their model in 2003. And their 2003 model uses the same factors, but weights them a little differently. They're putting less weight on the Harris-Benedict model, 0.85 times HB. Is that still a positive effect? Yeah, because it's still a positive number. You know, the bigger than one and smaller than one, that's exponential models. These are more of a linear type model. Plus 175 times your max temperature. That's still a positive effect. Plus 33 times your volume of exhalations minus 6,433. So you can see here what they did in 2003. Are they saying that the result of the Harrison-Benedict model, are they saying that it has more or less impact on your calorie expenditure? Less, good, because they went from 1.1 down to 0.85. They're giving it a lower weight. For your body temperature, are they saying now that they consider that to have more or less of an effect on your energy expenditure? More, because it's a bigger number. How about the volume of the air you inhale and exhale? More, just slightly more, but yes, more. So we've discussed the variables and how they affect things. We're going to be jumping down to number 3. Suppose Camilla and Sophia, who are female twins, want to calculate their resting energy expenditure using the Harris-Benedict equation. So they're going to be using the Harris-Benedict equation, HB for women. And they give their stats there, their height, weight, and age. So I want you guys to take a couple minutes, number 3, and go through and calculate their resting energy expenditure for each of them. And we'll discuss this in just a couple minutes. So this is number 3 in M8. Okay, so let's take a peek at this. So the Harris-Benedict equation for resting energy expenditure for women is the one I wrote down here. Let's look at Camila. For Camilla, it'll be the 655.0955 plus 9.5634 times her weight is 61 kilograms plus 1.8496 times her height is 165 centimeters minus 4.6756 times her age of 30. So 6.55.095 plus 9.5634 times the 61 plus 1.8496 times the 165 minus 4.6756 times 30. That gives us 1403.37. Okay. And I'm going to carry it right out to the 3789. I'm going to keep it all the way out there. Calories. That's calories burned per day. Now, rather than doing this whole formula again for Sophia, let's take a look at it. For Sophia, what's the only difference? Yeah, her weight is 62 instead of 61. Everything else is the same. Is increasing her weight going to decrease or increase her resting energy expenditure? Increase, because it was a positive relationship. Yes. It's going to increase it by how much? 1 kilogram is going to increase it by 9.5634 calories. So we just add that. That's going to be 3, 12, 14, 9. So rather than punching it back into that whole formula, Sophia is 1,412.9423 calories per day, because that was the only variable that changed. Does that make sense? Now, let's say that we have someone, that's kind of answering part B there as well. How much higher Sophia's predicted, and how does this relate to the equation? Well, we actually used the equation to find it. It's just the difference for 1 kilogram in weight is that coefficient for the weight. If their height was changed by 1 centimeter, how much would that change their resting energy? Perfect. Yes, it's their height times 1.8496. So that would be the rate of change as related to the height. So every centimeter of height difference would be 1.8496 calories. How about for age? Part C for number 3 is asking you to relate it to the age. How does the age relate to the calories burned? If a person's age goes up by 1 year, how does that affect the calories burned? Perfect. As their age goes up, as they get a year older, for every year older, they burn 4.6756 calories less per day on average. Okay, so now number 4 is just kind of a discussion question. Let's say that you have just completed a 45-minute workout and want to measure or want to estimate your resting energy expenditure. Do any of these equations take into account the fact that you just worked out? Well, let's look at the first one, the American College of Chest Physicians. That one is saying the resting energy expenditure is 25 times the weight. Does that include anything that might be affected by your working out? No, not really. Oh, sorry. They're asking if you just completed a 45-minute workout and you want to estimate your resting energy expenditure now, do any of these formulas consider that you were just working out? Well, this is the first formula from the American College of Chest Physicians. Is there anything in that formula that would take into consideration that you just worked out? No, your weight isn't going to change significantly in the workout. So that doesn't consider anything. Now, I'm just going to jump up to the Harris-Benedict equation up here. Is there anything in that equation that would take into account that you had just worked out? Is your height or weight going to change, or your age? No, not really. Well, let's look at the Penn State model. The Penn State model, I'm just going to use the 2003 model. They both involve the same factors, just different numbers in front of them. Your resting energy expenditure of 0.85 times the Harris-Benedict factor plus 175 times your max body temperature plus 33 times your volume of air exhaled and inhaled minus 6433. Now, we've already said the Harris-Benedict factor. There's nothing in that would be affected by you working out. Either of these other factors, could those be affected by you working out? Can working out affect your body temperature? Definitely. Can it affect the volume of air you inhale and exhale? Definitely can. So actually working out will affect both of those. So if you wanted to estimate how much working out changes your energy expenditure for the day, the Penn State model would be the one you'd want to use because it considers your body temperature and your change in volume of exhalation. Okay, so the final thing that they want you to do here for part one, for problem one of this unit, of this exercise, and what I'm going to do is I'm going to give you like 7 minutes to work on this, and then we'll take a break. They want you to pick on, this is number 5 now in M8. They're giving you 2 profiles. Profile 1 is a male, age 29, 188 pounds, 5'11", 98.6 degrees Fahrenheit body temperature. Exhalation, volume of exhalation is 7 liters per minute. Profile 2 is female, 25 years old, 147 pounds, 5'6" 98.6 degrees Fahrenheit, and 6.7 liters per minute of exhalation. There are some issues here, though, because weight for these formulas has to be given in what unit? They want it in kilograms. We're giving you the weight in pounds. Can anybody recall for me how to get from pounds to kilograms? To get from pounds to kilograms, the conversion factor is, and they give it back earlier in the unit, see which one they're using. I usually use 2.2. I want to make sure they're using the same one. I don't see it now, so we won't worry about it. To get from pounds to kilograms, it's your weight in pounds divided by 2.2 gives you your weight in kilograms. So you would have to divide by 2.2 to turn those into kilograms. Height is given in feet and inches. For the formulas, we need height in centimeters. So we need to convert those. Now I'm going to give you an example. I am 6'2". If I needed to convert my height into centimeters, what would it, can anybody tell me what I should do? Well, first, okay, what times 2.54? There we go. My height in inches times 2.54. So first I would have to do 6 times 12 is 72, and then add the 2 to it to get 74. So it'd be 74 times 2.54. And then the final thing we had to do, the body temperature, Tmax, the formulas want it in degrees Celsius. We're given in degrees Fahrenheit. So let's say that, let's just do this conversion. Our Celsius temperature is equal to our Fahrenheit temperature minus 32 times 5/9. So they're given this one as 98.6 Fahrenheit. We'd subtract 32 from that, and you just complete that formula. I'll let you guys take it from there. Get your temperature in degrees Celsius. So I'm going to do it's 11:17. I'm going to give you guys a few minutes to work on it. Then we'll take a break. Then we'll see how we're doing. If you need a couple more minutes to work on, pick one of those. You either pick profile 1 or profile 2, or if you would like to do your own information or make up your own information and put in there, that is fine as well. What they want you to do down below, they want you to calculate the resting energy expenditure. If it was American College of Chest Physicians, then they want you to use the Harrison-Benedict equation, and then they want you to do both of the Penn State equations and compare how the resting energy expenditure is different from one to the other. It works better if you use either profile 1 or 2, by the way. But if you want to put your own information in there as profile 3 and use it, that is fine as well. I'm not sure if any of you know what your liters per minute on your respiratory rate is, but go ahead and, like I said, we'll pause this here for you. We'll work on that, then we'll take our break, and then we'll talk about it more. So for now, I'll give you a couple minutes to work on these and get started on it. Anybody have any questions on what they've done so far? Okay, let's take a short break if you want to. Come back and work. Let's get back by 11:30, and we'll work some more on this. Let's just take a look at how you're doing on these. How many of you chose profile 1 to do? Just a show of hands. Nobody? How about profile 2? You're still working at it? Oh, sure. Yep. Let's give you about 3 more minutes, and then we'll come back then. You bet. Okay, let's see how you're doing. For profile 2, what did you get for the energy expenditure for the American Academy of Chest Physicians? There might have been slight round off. I got 1667, but that might have been just round off in the. Oh, yeah, they're using a little bit different conversion factor for kilograms. That's what it is. So the 1,670, that sounds good. For the Harris-Benedict, okay. That sounds reasonable. They're giving 1,486. So again, that's just round off in our conversions. That's actually not that large of a round off error. So then I'm just going to give you the Penn State ones. For the 1998, it's 1691. 2003, it's 1528. Now you can see there's quite a range here. 1486 to 1691, that's over 200 calories a day difference in the estimates. So the question is, how accurate do you think these are? Well, if I pick an individual person and I apply this formula to them, do you think I'm going to be close to what their resting energy expenditure is? Probably not necessarily. No, there's a chance I might, but most likely not. But let's say I pick a group of 20 people and I apply one of these formulas to all 20 of them and I average it out. Do you think that average that I get, my estimated average, is going to be close to the real average for that group? Well, if you think about it, I mean, some of the people in that group of 20 will probably burn fewer calories than what the model says, but some of them are going to burn more calories. So there's a good chance that with that group of people, they're going to average out to be really close to the estimate. Remember, these estimates are giving an average person, and of course, what really is the average person, right? Okay, so this is an example where, except for the American College of Chest Physicians, there was multiple variables. It's called a multivariate model. And in the real world, more often than not, there are multiple variables that come into play. You know, we had a model here where that resting energy expenditure had a number, and I'm just going to put in some rounded numbers. I'm going to use the one for the Harris Benedict, the men, was 66 plus 13.7 times the weight plus 5 times the height minus 6.8 times their age. For this model, each item, it's multivariate. There's several variables that come into play here, but it's also linear in each variable. And I'm going to say linear sort of, because this here, the 66, is kind of like our y-intercept. If they weigh nothing, have no height, and have no age, that would be what we would estimate their calorie expenditure at, which of course is not a very reasonable number. But what to say this is sort of linear, if we assume that the height and the age don't change, well then this becomes a linear equation in terms of the weight. And that's what, in the real world, that's what we often have to do. My background before I started working here at WITC, my background was as an engineer. And in many of the things I did, there were several factors that came into play like this. So we had to pick the factors that we could control and that we could keep constant. Like we could control the weight of plywood going on the roof, and we can control the weight of shingles. So we would make those numbers. So here, if we had a person that was a certain height and they're a certain age, we can keep them at that height and age and then see what happens if we change their weight. And that's what happens in the real world is we take models like this have multiple variables, then we try to assign values to some of those variables to make them easier to work with. Okay. Next thing is not all of these multivariate models are linear. So the next model we want to look at is a model for kinetic energy. This is problem situation 2. It's the tennis ball versus a car. We're talking about kinetic energy, which we're just going to abbreviate with K. The model we've probably been more familiar with in physics class or anything like that is 1/2 mv squared. They're using 0.5 times the mass times the velocity squared, where your mass is in kilograms, your velocity is in meters per second. So that's your speed moving in meters per second. To work with this problem, one of the first things we're going to need to do is we're going to need to be able to turn anything in weight or gram, weight in pounds or mass in grams into kilograms. We've already looked at, kilograms is equal to pounds divided by 2.2. And that's close enough for our numbers. Actually, the one they used in the book, let's use that one. The one they're using in your materials is your kilograms is equal to your pounds times 0.4536. Just think of trying to enter this in quantity, it's probably going to want it done with that conversion, which will be a little bit different for a round off. The more important is your velocity. It has to be in meters per second, but let's say we have a car going 60 miles per hour. Our unit conversion to convert that into meters per second. Well, 60 miles per hour is 60 miles over 1 hour. Written like that, now we can use our unit conversions or dimensional analysis to convert the units. We have to change miles into meters, and we have to change hours into seconds. Well, the hours to seconds is pretty simple. I'm trying to look to see here if we have anything for miles per hour. Oh, they do give us 1 mile per hour is equal to 0.447 meters per second. So they're going to make it easy on us and just give us this conversion. So we just take 60 times 0.447, which would give us 26.82 meters per second. Okay, so what I want you to do, they're looking at problem number 7 here, part A. They want you to compare the kinetic energy in joules remember that kinetic energy is 0.5 times the mass times the velocity squared. They want you to compare for a tennis ball that has a mass of, where is it, 58.5 grams, and a velocity of 50 miles per hour. To a car that has a mass of 1,500 kilograms and a velocity of 65 miles per hour. Now in our formula, what does mass have to be in? Kilograms. So the car is good, that's already in kilograms. We have to convert the tennis ball, has to be converted into kilograms. To go from grams to kilograms, remember it's 1,000. So it's just a matter of moving that decimal point 3 spots to the left. So that would be 0.0585 kilograms. Have a good day, Sarah. No problem. We'll see you on Monday. Okay, sounds good. Okay, so then we've got that in kilograms for the tennis ball. And then we have to also convert both of these velocities into meters per second. which is just that number I gave you up here, the 0.447, to convert those. So what I want you to do is I want you to find the kinetic energy for both the tennis ball and the car. I'll give you a couple minutes and then we'll talk about those. So if we take a look at these, first thing, of course, we had to convert the miles per hour into meters per second. So the tennis ball, 50 miles per hour is 22.35 meters per second. For the car, 65 miles per hour is 29.055 meters per second. So then for the tennis ball, our kinetic energy is 0.5 times the mass of 0.0585 times the velocity of 22.35, which gives us 14.61 about. Perfect. That's going to be in joules, what energy is in. So then for the car, that's 0.5 times 1500 times the 29.055 squared. What'd that give you? Now we're going to go at 0.8 because they're in the room. Joules. So significantly more. Now the car weighs a lot more than the tennis ball. 1,500 kilograms to 0.0585 kilograms. Significantly larger there. But it's also going faster. And that speed is, that velocity is squared. So in this model, it's not linear. The different items have a heavier effect. So let's take a look at a car. A 1,500 kilogram car. And we are going to go from 25 miles per hour up to 50 miles per hour. Now what I want you to do is I want you to find the kinetic energy of that car at each of those speeds. Remember, you have to turn the 25 miles per hour into meters per second. So I'll give you guys a couple minutes to do that. Convert those over and find those kinetic energies. So it's going to be 0.5 times 1,500 for each of them. That'll be the velocity squared. So for both, we got to convert the miles per hour to meters per second. So the 25 miles per hour becomes 11.175 meters per second. 50 miles per hour is 22.35 meters per second. So for our kinetic energy, for the first car doing 25 miles an hour, it's 0.5 times 1,500 times 11.175 squared. What'd you get for that one? Okay. And that's joules. For the second car, then, it's the 0.5 times 1500 times 22.35 squared. What do you get for that one? 0.88 joules. Perfect. How do those compare to each other? Obviously, this one's quite a bit bigger. But if I were to divide them out, if I divide those, what do I get? Yeah, it basically comes out to be 4. Doesn't make sense that that would be 4. Well, think about it. What we did here, what value did we change? Did we change the mass? No, the mass stayed 1,500 pounds or 1,500 kilograms per car. Did we change? We changed the velocity. And what did we do to the velocity? We doubled it. So that would make sense that something would double. Only the problem is this isn't a linear relationship. It is velocity squared. What's 2 squared? 4. What do you think would happen? Oh, go ahead. All right. Yeah, we just doubled the velocity, but since it's squared, that increases the energy by a factor of 4. So what do you think would happen if we sang our speed up to 75 miles per hour? From the 25 miles per hour, now we've tripled it times 3 for the velocity. What do you think that's going to do for the kinetic energy? Well, if doubling the velocity multiplied the kinetic energy times 4, what do you think tripling the velocity is going to do to it? What's 3 squared? It should be times 9. I want you to go ahead and figure that out. Find the kinetic energy. See, because it's squared. Okay, actually, I was going to have you find that kinetic energy quick, but I see we only have 15 minutes left. So I want to make sure we get through a couple of things here first. The next situation is talking about evaluating car sales or buying cars. And they're looking at the reliability versus gas mileage versus interior comfort and cargo space for cars and giving them rating. So this is problem situation 3. And they have those 3 cars there that all have their ratings set out. And then they've done an average for each. Car 1 had ratings of 8, 6, 5, and 7, which gave an average of 6.5. You guys remember how to find an average, right? Just add them up and divide by, there's 4 there. Well, car 2 had its ratings and an average of 6.5. And car 3 had its ratings and an average of 7, slightly higher than the others. So does that mean that car 3 is the better car and that's the one you should buy? Well, not necessarily. We look at the things that we have here. The top number is the reliability of the car. The second number is gas mileage. The third number, I'm just going to abbreviate as interior, features and comfort, just interior I'm going to write. And the last one is cargo space. Well, if you look at car number 3, it actually has lower ratings in most categories except for the cargo space. It has a huge cargo space, and that's what gave it the higher average. What if you're a person who doesn't need a lot of cargo space? So to account for that, we use weighted averages rather than averages. And weighting is basically assigning an importance to an object. And you might, do whatever. You might have 10 points that you want to split up between them. You might have 20 points, 100 points that you want to split up. Let's say you look at this and you pick which one of these is the least. Let's just go through and figure out some weights for ourselves. For you guys, which one of these 4 features would be the least important to you? Cargo space. So let's assign that a number 1 for now. What would be the next least important? The features, okay. So let's, it's a little bit more important. Would you say, is it twice as important as the cargo space? Let's do this. Let's make it easier. Let's assign the cargo space a 10. If cargo space is worth 10 points, how much more important is the interior comfort and features? A 15, a 12, a 20? 15. So a little bit more important, but not a lot. Okay, let's look at the remaining 2, reliability and gas mileage. Which one is the most important to you? Reliability. Where would you put that? Like 3 times more important than cargo space? 4 times, 30, a 40? Don't be shy. Well, we're just trying to say how important it is. If you're saying cargo space is worth 10 points, how many points would you put on reliability? Let's just throw 50 points on there. Because that's saying it's a lot. It's 5 times more important than the cargo space. How about gas mileage? Where does that fall in there? Is it a little bit more important than interior comfort or a lot more important? So maybe give it like a 25, a 30? Or is it closer to reliability? Is it like a 40? Maybe gas mileage and reliability are equally important? Okay, let's do this. We're going to drop this down to 40. So now what we have here is we've just assigned points. And if we added those all up, it actually adds up to 105. We could adjust them if we wanted to make them add up to 100 or whatever we want them to add up to. It really doesn't matter. All that is saying is, really, this could be a 1 and a 1.5 and a 4 and a 4 if you wanted it to be. All that it's saying is reliability is 4 times as important to us as cargo space. And about 2.5 to 3 times as important to us as interior features and comfort. So what it's telling us now is, looking here, like car number 2 has a high rating for interior comfort, a low rating for reliability. So that one's going to get hurt a lot because that's the one that we really want. So what they're going to give us is they're going to give us a weighting here. I said I'm kind of breezing through this a bit. They developed this concept a little more of doubling or whatever. What we're going to do is we're going to actually flip up to question number 12 here. And question number 12 they actually assign a weighting strategy to these things. And they're going to give different weights to them. He's developed a formula, and this is a weighted average formula with the car quality. And they're using a 40-point scale. So they've assigned 0 to 40 points divided up amongst these 4 features. So their car quality factor here is 10 times the reliability. What that is saying is the reliability is considered, worth 10 points of importance, plus 5 times the gas mileage. Gary in this problem must have a lot of money if you don't care about gas mileage. That's a pretty low number. Plus 20 times the interior comfort. So is that saying he thinks the interior comfort is really important or not important? Well, that's a big number, right? He's saying it's really important. And then 5 times the cargo space. So Gary doesn't care much about cargo space either. So you can see here, Gary is mostly concerned about comfort. So again, probably has more money than I do. The 40 on bottom comes from adding these factors up. That adds up to 40. So we're doing that on part C there of number 12, is we're making a table. And the table is going to have the weights and then the rating. And the weights that are given are 2, 1, 4, and 1. Actually, sorry, I'm going to give the weights out of the formula. That's the first one. That's the old weight. So the formula is 10, 5, 20, and 5. And I'm just going to go through car 1 quick. If we flip back to car 1, car 1 had a reliability of 8, gas mileage of 6, interior comfort of 5, and cargo space of 7. So to find its weighted average, we find the total of the weights, which is the 40, and then we multiply each weight times its rating. 10 times 8 is 80, 5 times 6 is 30, 20 times 5 is 100, and 5 times 7 is 35. We total those up. If we add those all up, we get what, 245? Is that total? So our weighted average is found by taking this total divided by the total weights. So 245 divided by 40 is 6.125. So that was car 1. We have a couple minutes, so let's compare car 2 quick. Car 2's ratings were 6 for reliability, 7 for gas mileage, 9 for comfort, and 4 for cargo space. So we're going to take the weight times the item. 10 times 6 is 60. 5 times 7 is 35. 20 times 9 would be 180. 5 times 4 would be 20. That all adds up to 295. But we're still going to divide by that total weight of 40, which is going to give us 7.375 as that rating. So what this does is it's saying it's giving the most importance to the comfort, the interior comfort. So because car 2 had a much higher rating for interior comfort, it ended up with a higher average, even though it was lower in reliability and much lower in cargo space. It still had a higher overall rating because to this person, comfort was most important. One of the examples is GPA. GPA, let's say that you have different classes. You have credits and you have your grade in that class. Let's say you have a 4-credit class, a 4-credit class, a 2-credit class, and a 3-credit class. And I'm going to keep it simple. I'm not going to use pluses and minuses. Let's say you get an A and a B in your 4-credit classes. You get a C in your 2-credit class and a B in your 3-credit class. Your GPA would be calculated. Of course, you got to find assign the numbers to the grades. An A is a 4, B is a 3, C is a 2, and B is a 3 again. That's off the grade point scale. Our weighted average is our GPA. We're going to first add together all the credits. 4 plus 4 plus 2 plus 3 is 13. And then we're going to do credits times your grade point. So 4 times 4 is 16. 4 times 3 is 12. 2 times 2 is 4. And 3 times 3 is 9. I know I'm flying through this kind of fast. Are we with me so far? Okay. So we add up that total. So 16, 28, 32, 41. And we divide the 41 divided by the total weights of 13. 41 divided by 13 is like 3.15 something. I'll do it out here. 41. 3.15. It's close enough. That's the GPA. If we need to spend more time on Monday going over weighted averages, we will. I flew through that kind of fast. Due for tomorrow, for Thursday, remember, is the out of class exercises for M7 and the preparing next lesson for M8. Due for next week, Tuesday, is going to be the out of class exercises for M8. Again, if we have to go over some of these more, we will. There is no preparing for the next lesson. On Tuesday, we'll wrap this up and we'll go over more of this as we need to. And then we'll make sure we do a review on Tuesday. Next Wednesday, we're going to do our test for Module M for our modeling. So we'll make sure we do have some time for review on Monday. The test is paper and pencil. It won't be in Quantway. So I'll have it sent out to your locations. So it should be ready for you in the classroom when you get there on Wednesday. Okay, you guys have a great weekend and we'll see you on Monday. You bet.